All right, so last class we finished 13.6, which was surface integrals. Well, sorry, it was parametric surfaces, right? Parametric surfaces. And we concluded as parametric surfaces by evaluating this integral, this double integral, which gives us the surface area of a surface, right? Now this is we're going to continue with this concept into the next section. 13.7 is heavy in terms of the amount of stuff in it, all right? We'll see how far we get. I still am cautiously optimistic that we can finish the book. I don't know. It's going to be close. So we're going to go in 13.7 now. So now we're going to talk about surface integrals. So in the previous section, all we did is we said, okay, if we have a surface, right? If we have a surface, we can find the area of that surface. That's all we did. Now what we're doing is, think of this in terms of, remember when we had a vector function r of t, and that drew some curve, right? And let's say this is three-dimensional space. Doesn't have to be two. And then remember we were talking about like the mass of a wire or something? What we were doing is we were saying, okay, if somebody gives us like a density function, r of xy or xyz, let's make it two-dimensional. Then if I know the density at each point, then I can basically sum up all the masses and then find the total mass of this. And then we can also find center of mass. The idea, though, is just that you're integrating over some curve, and you're integrating some function, f of x, y, which basically gives you the value of the function on that point, whether it be the mass there or it be the temperature at that point. Doesn't matter what it is. We're using the integral to add up the value of some scalar function as you move along this curve, right? dr. So that's what we've done in the past. Moved along the curve and added up all the values of some scalar function along that curve. We're going to do the same thing now, except we want to move along a surface instead and add up all the values of some scalar function on that surface. So that's what a surface integral is. So there's the, where's my, you'll see the rag anywhere? Is that it? That's the only one? So first the definition. Okay, so we have this is new. Double integral over some surface. Okay, that's not new. We did that last class, double integral over some surface. But now what we've included is this scalar function, which would be like the density function or something like that. This is the function that we're going to evaluate at every point along that surface. And then it's with respect to capital S. Do not confuse this with little s. Do you remember? Oh, this should have been little s over here, sorry. Do you remember what little s was? Little s was something else. Arc length. This was arc length. So you're adding up along here. If we take this out, that just gives you like the length of the curve. If we put this in here, then it's going to give you something else. That's exactly what's happening here. If we put a scalar function, if we take that out, this is just the surface area. Do you see what's in yellow? That ds represents this, and that's the previous section. This is the cross product of the partials, magnitude, and then times dA. So we're just adding this new layer to the integral, this scalar function in front of the surface area. All right, so let's do an example. And let me write that formula down over here. We had the double integral over S of our scalar function f of x, y, z, d capital S. Man, that's a terrible marker. Okay, which is, in this case, I'll leave it right there. We can just do that. All right, so we've got our scalar function. Everyone see the scalar function right here? This right here is our f. And we want to be integrating over the surface S, where S is the part of the unit sphere above the cone, z equals square root of x squared plus y squared. Okay, maybe we should talk about what S is first, right? Like try and draw it maybe. So we have the unit sphere, and it's the part of the unit sphere that is above this cone. So do y'all know what this cone looks like? Like what do you get if you plug in 0 for x and y, what do you get for z? 0, right? So you're at the origin there. And then what about if you let y be 0? If y is 0, you get, technically z is the absolute value of x, because when you take square root of something squared, technically it's the absolute value. So it would look like a v, wouldn't it? And if you let x be 0, then you get z equals the absolute value of y. It's a v in the y direction as well. So it's a cone, right? So we have a cone that comes up like this. You know, it goes forever. But we're trying to find the surface integral over the surface where that cone hits the sphere. So it's going to be something like this little patch up here. Do you all see that? That's our S. Understand? So we're taking that surface S, and what we want to do is we want to imagine that, you know, along S there's infinitely many points, right? There's points all over this S. And what we're doing is for each one of those points, we're plugging it into the function and getting some number, right? And we're adding them up. So at every point along that surface, we want to add up the value of the function there. And again, if this was like density or something like that, we could get a total mass. Okay, but that's visually, hopefully that makes sense what we're trying to do. So let's set it up. Any ideas?
Set up the pyramid.
Set up the, so you want to draw the surface?
Yeah.
Draw the surface, yeah. So if we're going to do this, right, what this says is we have to take our surface, right, S, and we have to find the parametric representation of that surface. We have to find it in terms of some vector function, r of u v. So we have to draw the surface with r, and then evaluate our function, our scalar function, evaluate it on that surface, take that, multiply it times the magnitude of the cross products of the partials dA. Now, what's the domain D here? D is the restriction on what for us? U and V. It's the restriction on U and V that draws us the surface. Okay? So yeah, I say we start with the surface. Let's try and figure out how we can draw this surface. So for S, I'm going to draw it with some parametric vector function, let's say. Okay, how do you draw a sphere? Because it's part of a sphere, right?
X squared plus y squared plus z.
Okay, so that's the good old equation, right?
Yeah.
But we want it as a vector function. So we're going to have to use the cosine, theta, sine, phi. Remember all that?
Yeah.
Okay, but we're not going to use theta and phi. We're going to use u and v. Okay, so let's see if we remember what it is. Do y'all remember? It's cosine u, sine v. So v is phi, right? U is like theta, v is like the phi, right? Okay. How do we do phi? Okay, that's not important, but okay, and then it's sine u, sine v, cosine v. Sorry, I thought I heard u. Okay, that should draw us the unit sphere. Now, unit because, right, the radius is 1. So that's our rho. Our rho is here. Here is 1. That's how we draw a sphere. Now, restrictions. U and v. U is theta, right? V is phi. Okay, you have to be extremely careful here. Because do we want to draw the whole thing? No. We only want to draw this top little piece right here, right? Shit, how are we going to do that? How are we going to do that? Let's look at a cross section. Imagine cutting through this and looking at a cross section of this. It would look like a circle, right, like this. And then it would look like our V comes out like this. Agreed? Yeah? Okay. So can you all imagine that if we had the x, y, z here, remember with spherical, the phi was this, so that's v for us, right? And then the theta is this, right? And that's the u for us. So if I only want to draw that little top cap up here, right, then my phi needs to be restricted, doesn't it? My phi needs to be restricted from here to here. My phi, whatever, right? That needs to be restricted. And then my theta can what? Swing between 0 and 2 pi. So that, the u is the theta. That can go between 0 and 2 pi. But my v has to be between what? Straight up, which is what? 0. Well, that's 90, but with phi, it's measured from, that's 0.
Okay.
Yeah, that's 0 up here, is 0 for v. And then that would be pi over 2, and then that would be pi. So we want to start at 0 and go to, well, what is it? Pi over 4. How do you know? You have to convince yourself that it's pi over 4. You have to know that this hits at a 45-degree angle. How do you know it does? Well, where do these hit each other? Where does this cone hit the sphere? How could you check? Set them equal to each other. So this is where you would bring in that equation that you were talking about earlier. The equation of the sphere is x squared plus y squared plus z squared equals 1. That's the sphere, right? And then the cone is z equals the square root of x squared plus y squared, right? If we take this and replace it here, what would we get? So I'm going to plug that into there. We would get x squared plus y squared plus x squared plus y squared equals 1. And that's 2x squared plus 2y squared equals 1. So x squared plus y squared equals 1/2. So yeah, so you would, one way you could think about it is if I were to try and find this angle, I could say this is x. Let me just say use the x-axis and then the z, right? If I'm looking on the xz plane, then what's y? If I'm on the xz plane, I cut through here on the xz plane, what's y then? 0. So what would happen if you replaced y with 0 here? X squared equals 1/2. And then you take the square root on both sides, and you get x is plus or minus 1 over root 2, which is the same as root 2 over 2, which is the x-coordinate on the unit circle at 45 degrees. So there's a lot there that I'm kind of glossing over, but that's how you convince yourself that it's pi over 4. Okay, yes, we have S. So now, what do? Erase. Not that though. So I want to set up this right here. This is our domain restriction D, right? That's our domain restriction. And we're going to set up this double integral. So it's going to be double integral over D. I'll fill in D later. I want the original function, the scalar function, which is this, evaluated on the surface. So that means I'm going to replace x with cosine u sine v, replace y with sine u sine v, replace z with cosine shit, right? So you've got cosine u sine v, sine u sine v, cosine v. That's x, y, z, right? Oh, z. That's your scalar function, x, y, z. Now we need what? ds, the cross product of the magnitudes of the partials of this, which we did last class. So I'm not going to do it again. But you understand what you have to do, right? Take partial of this with respect to u, take partial with respect to v, cross them, take the magnitude. Do you all remember what we got?
It was, do you want the magnitude or just the cross?
Magnitude.
The magnitude was,
And it should look familiar to us too. We did it when we were trying, look at the work that we did when we were trying to find the surface area of a sphere, and we proved the surface area of a sphere of radius r. What do we get at the very end? Or at that cross product part?
For that question, we plugged in the numbers for the radius of the sphere.
Now we found the surface area of a sphere of radius r. It was arbitrary. Yep. It was r squared sine v. But for us, what's the radius of our sphere? 1. So if you took the partial of this with respect to u, then the partial of that with respect to v, and you crossed them, and then took the magnitude, everything would simplify and you would get sine v. Sine v. So that's what this becomes right here. All of this right here becomes sine v without showing the work. Okay, so this part right here is the magnitude of the partials. And then dA. We all right? Yes, life is not good. All right, let's go ahead and put our limits of integration. The order doesn't matter because my limits are constant, so I'll go 0 to 2 pi for my u, and I'll go 0 to pi over 4 for my v. And then I can kind of clean that up a little bit. I've got, let's do the u's first. I've got a cosine u, sine u, right? And then in terms of v's, I got sine cubed v, and then a cosine v. And then this is d, now I have to do this right. D, what's the inner integral? Yeah, it's dv du because v is the variable, it's like the phi was. All right, there we go. We just have to do that integral. And I'll also point out, I mean, we could do this now, right? It wouldn't be that fun, but we could. I'm going to point out here that notice that our u's, our stuff with u's and our stuff with v's are separated with multiplication. And because of that, I can use that special property where I break it into two integrals, where I do the first integral would be the ones with the u's, 0 to 2 pi cosine u sine u du, and then times the other integral, 0 to pi over 4, and then I could do sine cubed v cosine v dv, and multiply those two answers. That can only ever be done, right, if you can separate the two variables completely like that. And then, I don't know, this is pretty straightforward, right? I could do a basic u sub here. I would let u be sine u. Well, I couldn't let u be sine u. I have to use a different variable. But I could do a basic substitution here. W is sine u, and figure out that. And then this one, I could let, I don't know, q be sine v, and then derivatives right there, right? Okay. So I'm not going to go through this. The whole idea here is, can we get to this, right? Because at this point, it's just mechanical stuff. And so if we went to Wolfram or Symbolab or something, I believe the answer is, no, it's not pi. Is it pi? I don't remember. Should we look it up, or are we happy? I mean, should we type it in? Let's type it in, yeah. It won't hurt. Let me get my, can I take this one? I was going to type these up before class and have them all ready, but I was like, you know what, I'll just do them in class if they want to see it. So we'll do, I don't ever use Symbolab, but, okay, we're going to do, I'm going to do them all together. I'm not splitting it up. I'm going to do both integrals together. So the outer one goes from 0 to 2 pi. Inner one goes from 0 to pi over 4. And then we have cosine u sine u, and then sine qv, I'm going to do it this way, sine v cubed cosine, right, v, oops, dv du. Oh, it's 0. Okay, you get 0. You're squinting. Seem weird? Seems weird, right? 0? Yeah, let's see if we can reason it out. why the answer is 0? Okay. It has to do with the problem in the picture and most importantly, the function, the scalar function f. So what is f doing? What is our scalar function actually doing? It's taking the x-coordinate, the y-coordinate, and the z-coordinate and multiplying the 3 together, right? Now, when we're on that little dome, now, that's not good. Remember, we were on the sphere, and we're this little patch on the top, right? Like this. There. That patch right there, right? We're on the top of that little patch. Let me take out everything else. Whoa, why didn't it go away? There it is, right? So we're on that little patch right there. And what we're doing is we're multiplying the x-coordinate, the y-coordinate, and the z-coordinate, and we're adding them up. We're adding them up. So let's look at this from the top. Let's look at it from the top like this. And remember the x-axis, red, right? Green. That's your x and y axis. And let's say this is the x positive direction. This is the y positive direction. Now, do y'all agree that the z-coordinates are always positive because of where we are, right? We're above the ground. Okay, so if I were to pick a point, let's say in the first, this would be the first quadrant, second quadrant, third, and fourth, if we're looking at it two-dimensionally. If I pick a point right here on that red surface, I'm going to take the x, the y, and the z and multiply them together. That's going to give me a positive number, right? So this point, right, the contribution of that point is x times y times z. All right? That would be a positive number, right? But that's going to get canceled out by what? Where? What quadrant? Let's go quadrant 2. So if we go out a certain amount here, we go up, right? Let's go this way, the same amount, and up right there. Okay, tell me what's different here. The x is now negative. Is the y the same? Z the same? Yes. So those two will cancel each other, won't they? Yeah, and that would work for any point here, right? Any point here will cancel with its partner over here in this quadrant as well. Yeah? So these two are going to wipe each other out. Then when you do something in the, let's say, third quadrant, let's pick something here. Now the x is negative, right? The y is negative, and the z is positive. So you get negative, negative, positive. That should be a positive number. And then when you're over here, what happens? Your x is positive, your y is negative, your z is positive. So that's a negative. They cancel each other out. So it's all based on the symmetry of the problem, the symmetry of the shape, and the function itself, f of x, y, z equals x, y, z. If we change that formula, x, y, z, tweaked it a little bit, we lose symmetry. I mean, we don't lose symmetry of the shape, but the canceling would be lost. Does that help clarify why it's 0? Yeah? Yeah.
So that would just be let's say that was a question, that would just be the final answer.
Yeah, that's your answer.
Okay.
Yeah.
George was also saying that the first integral from 0 to 2 pi of cosine u sine u, that's 0.
Yes.
So then 0 times whatever that is.
Oh yeah, this integral right here is 0. Absolutely. But I thought the question was why are we getting 0? Like not so much of like, yes, this is 0, but more of like geometrically, why is it 0? Like we're adding up the value of the function along a surface. Shouldn't we get a positive number? Well, it depends because when you add up the value of the function's going to spit out some positives and maybe some negatives. And if they wipe each other out, it's kind of like when you do a double integral in Cal 2, I mean a single Cal 2 integral, if you just integrate sine, right? The sine function. If you integrate it from 0 to 2 pi, what's your answer? 0, right? Because this area cancels out this area. It's similar. Okay, yes?
I remember I was actually watching your Cal 2 videos. You had mentioned that to get the actual true area, you have to move the restrictions, but it says...
Wait, to get the true area.
So like, yeah.
Oh, yeah. So like go from 0 to pi.
Yeah, well we can do that here.
You could.
Well, our domain is restricted already.
Yes, but if you wanted to know, like, you could do this quadrant alone, right? And it would then you wouldn't get 0.
Yeah.
And then you could say, all right, if you wanted to look at this more of like a net value, then you could say whatever this is times 4.
Yeah.
But that's a little different than the sine one,
Yeah,
because
those are
it's area. This is not really area. It has some other meaning to it,
Okay.
right? It's not an area. So we're not looking like an area below this surface.
Yeah.
It's actually like in another dimension that we can't see.
Okay.
Okay, good, great questions. All right, let's continue. So one of the nice results of this formula, right? One of the nice results is something we already know, and that is if the scalar function in front, if that scalar function in front is just 1, right? If that's just 1, then we get 1 ds. So the double integral over S of 1 ds should just be the surface area of S. This is a theme that we've just been continuing to see over and over and over and over, right? And now we can add this to it, right? The double integral over surface S of 1 ds should just be the surface area of S. All right, what are some applications of this? Well, I just said, if you're given a surface, some sheet, and you're given its density function, the density at each point on the sheet, then we can find the mass by doing the double integral over that surface of the density function ds. And that'll give us basically the sum of all the mass points, gives us our total mass. And then you could use moments and things like that, like we did prior, and we could figure out what x bar and y bar are. And z bar, sorry, we could find the center of mass of a 3-dimensional surface. Previously, we were able to find the center of mass of a 3-dimensional solid. Now we can do it for a surface in 3-dimensional space. We're not going to do any examples of this. This is just to show you you could. Like, it's just an extension of what we've already learned. All right, now we want to see the handout from last class. Now, I have some handouts here. Unfortunately, I didn't bring copies of the exam, mini exam. You know how I said, here's the old final? Who was not here last time? You need it, and who else? Anyone else? Everyone else was here? So I'll get you a copy of that. I know last time I didn't have these parametric surfaces. I have a few copies. Do you want one? It's not. It's unfortunately, it's black and white. Is that all right? Okay. And then anyone else need this one? No, the one where we practiced drawing surfaces. It was this one.
Oh, I didn't get that one.
You didn't get that one? Okay, I have one here. It's black and white. And I believe I worked it all out on here, so that's an old one. You can have that one. Okay. All right, so now what we're going to do is we're going to look at the other handout I gave you last class that said surface integrals, 13.7. And everyone have this one? It's in color. It's real pretty. This one. Anyone need it? You forgot yours. Okay. Just leave $5 on your way out, please.
All
Thank you. All right, let me bring this up. Where the hell's my mouse? Whoa, stop shaking. Where is it? There it is. Okay, here we go. Y'all ready? Buckle up. Y'all ready? So the surface integral that I just introduced you to, here it is, written in a slightly different way. So right now what we're looking at is a surface integral of some scalar function over some surface. Now, in this particular case that you're looking, the surface that we're drawing it with a vector function r of uv. So the u and the v are these two variables. They're almost like, they're not visible in our picture, right? You could look at them as almost like clocks, two clocks in the background, you could kind of say, are running that draw the surface, but they're not visible on our actual three-dimensional picture. The surface is visible, but its domain is not visible here. Okay? Do y'all understand that? Like I can't show you u and v on there. U and v is not in there. That's the result of the vector function over u and v, but it's not, I can't actually visually show you where u and v is in this picture. It's just running in the background. So when we have that, then we have our vector equation, right, that draws the surface, our domain d of that, the restrictions on u and v, and then this is the surface integral right here, double integral over s, the scalar function, right, ds. That means we take the double integral over that domain d, the scalar function evaluated along that surface, and then you do the magnitude of the partials and then dA, right? We just did a problem like that. But there are also 3 special cases where our surface is not this, but something else. So let me just scroll. So I'm calling this capital A, this formula, because as we move through some examples today, I'm going to ask you, like, what formula do you think we should use? Capital A, or should we use B or C? So let's look at formula for B. So what's the difference? Well, we still have a surface integral over some function, scalar function over some surface, right? Same thing. However, this surface, we're not going to draw it with r of uv. This surface is a good old-fashioned function of x and y, the way we started class. F of x, y draws you a surface. And so if we are given our scalar function, right, our scalar function, which is here, and the surface we're given is just z is some function of x and y, and I'm using g here, why, not f? I'm already using f here for something else, right? So this is just, it used to be f of x, y, but I have to use something other than f. So our z is determined by x and y. Z is a function of x and y. In this very special case, this is what it looks like visually. Our surface is here, right? Surface is floating. The domain this time has to do with x and y, so that domain is on the ground. I can actually see the domain in the picture, right? Because the domain is some, since it's a function of x and y, some function of x and y, the domain is just a projection of that surface onto the xy plane. So I can see it there, right? When we have this scenario, look at what changes here. Look at what changes. We're no longer evaluating f along the vector function. What are we doing? We're evaluating f. We're letting x just be x. We're letting y just be y. And z, we're replacing it with that surface. And then this changes. You know how that was the magnitude of the cross product of the partials? I showed the work here why this turns into this. If you were to take our vector function and treat it as, like, this is x and y, so x stays x, y stays y, and then your z is some function of that x and y. If you work through the whole crossing of the partials, at the very end here, you get this. That's the magnitude of the cross product of the partials. And you can see here, it's just the derivative of the g with respect to u squared plus derivative of g with respect to v squared plus 1. So I'm not going through this. I'm showing it to you here. I'm hoping you'll trust that that's what works out. So we just use this formula.